Okay, we're doing the practice test for integration. So what you need is the test, the formula sheet, and a calculator. I'm also just going to have the topic booklet up here because, well, I always forget the integration formulas. There's a lot to remember. First question is just straight up an integral. Make sure you're in radians for pretty much the whole test. And they're asking you to evaluate it on your calculator. So we literally just type it in. Cos x, take, this would be sine of x all squared. That's what it means when you have the squared in front of the sign. Close your brackets, and we integrate it from 0 to 1, and we get 0.5688. Now this one is actually possible to do by hand, but the question's not asking for it. Okay, now we get into the by hand integrals. We could write this as the integral of a half x plus 1 all to the power of a half. And then what we do is we go half x plus 1. We raise that power up by 1. Now we want to divide by 3 halves, but you can actually think of that as timesing by 2/3 instead. And we also want to divide by the number with the x, so that's dividing by a half. You can think of that as timesing by 2, so the whole thing just becomes 4/3 of a half x plus 1 to the power of 3 halves. Forgetting the plus c, and c is a real number. Okay, we've got this definite integral. So what we need to do is integrate from 0 to pi over 2. The identity that we want to use is that cos squared theta is half plus half cos of 2 theta. So I think that identity was in a topic booklet somewhere. Yep, there it is. So in our case, theta is 3x. So this is a half plus a half cos of 2 lots of 3x. So that's 6x. Okay, this will integrate up to a half x. Now that's going to become 1 over 12 because you need to divide by the number with the x, sine of 6x. If you ever really forget this identity, like if you forget to put it on your cheat sheet or something, you can rearrange the, I reckon it's this one, the cos of 2a formula, and you'll get it. Okay, why am I putting a dx on the end? That should just be the integral from 0 to pi over 2. Okay, so this is a half of pi over 2, so that's going to be pi over 4 there. And then 1 over 12 sine of 6 pi over 2. Take, and then we're going to plug in 0. So that's 0 plus 1 over 12 sine of 0. Now all that stuff on the end does go away because sine of 0 is 0. So you get pi over 4 plus 1/12 sine of 3 pi. And I reckon sine of 3 pi would be, might even be 0. So we might just get pi over 4. So let's check if this integral is correct. You absolutely should do definite integrals on your calculator to make sure. So we had cos of 3x. We're going to square that whole thing. And we're integrating it from 0 all the way up to pi over 2. And hopefully I get pi over 4. Yes, I do. Okay. You don't need to write square units since it's just a definite integral. This one here will become log of the absolute value of 2x take 1 over 2, because you need to divide by the number with the x, and then e to the 3x over 3 plus c. Some people might like to write this as half log of 2x take 1. Take a third e to the 3x plus c. C is in R. Both of these I would be very happy with. Okay. Next, we need to show this one. So this one we do cross multiplication. So we got 1 over x plus 4 times by x plus 2 over x plus 2. Actually, I might just write this. It's 1 over x plus 2 equals, now we'll do it. So 1 over x plus 4 times by x plus 2 over x plus 2. And then it's going to be plus 1 over x plus 2 times x plus 4 over x plus 4. And this is just cross multiplying. Since it's a show that question, it's good to sort of explain what we're doing in each step. So this will become x plus 2 over x plus 4 with x plus 2. Plus, and then this will be x plus 4 over x plus 4 with x plus 2. They both have the same denominator, so we can just add them up. X plus 2 plus x plus 4 over x plus 4 with x plus 2. And then that's what we want. So that should be 2x plus 6, which is what they're asking for. And they've got, and we can expand the bottom. So x squared plus 6x plus 8. So I might just go expand the bottom. And then you can just write as required. Okay. Hence do that integral. So this is the integral of, well, we can split up the fractions. So I might actually just write it formally. So 0 to 2 of 2x plus 6 over that thing. This just directly is that thing. So we can split it up into the two. So this is the integral of 1 over x plus 4 and 1 over x plus 2 dx from 0 to 2. So this is log of x plus 4 plus log of x plus 2. And we need to integrate that from 0 to 2. So this just becomes log of 2 plus 4, so that's 6. Log of 4. And this is log of 0 plus 4, so that's 4. And log of 2. Now, I've got rid of the absolute value signs because it's just 6 inside the log, for example, which is already positive. So the absolute values wouldn't have done anything. The log of 4s cancel out, so this is just log of 6 take log of 2, which is log of 6 over 2, which is log of 3. Yeah, we better actually make sure that we get log of 3 when we do it. Always double check your answers. This is part of the good thing about whenever there's a definite integral in a test is you absolutely can just check. Technically, you can check your real integrals too if you sort of evaluate the answer and then graph what you think the integral is. But definite integral is definitely a lot nicer to check. And yes, we get the right answer. Verify your answer using U substitution. So the integral from 0 to 2 of 2x plus 6 over x squared plus 6x plus 8 dx equals. Now, our U substitution will set U as x squared plus 6x plus 8, and du dx is 2x plus 6, which conveniently is the thing that's just on the top there. So this is U on the bottom and du dx on the top. And this goes from 0 to 2 sort of, it's x is 0 to 2. So I might just write x is 0 to x is 2, because now we've got like a few different things we might be looking at. This is the integral of 1 over u du. Now, if x is 0, u is 0 squared plus 6 lots of 0 plus 8, which is, let's see, 8. And if x is 2, u is 2 squared plus 6 lots of 2 plus 8. So what would that be? 4, 12, and 8 would give you 24. So essentially, this is u is 8 to u is 24. Now, you don't have to do it like this. You can keep it as like x values and then just sub back in your x. But by doing this, I never actually need to sub x back in. I can just plug my u values in straight away. This is log of 24, take log of 8, which is log of 3. So just be aware there are two different ways to do that question. I've subbed in particular u values. Okay, this one here, we've got a definite integral, 1 over that. So the integral from 0 to 2, 1 over root 16 take x squared. So this is, well, it's the integral from 0 to 2 of 1 over root 4 squared take x squared. And the reason I write it like that is we have some formulas for integrating to arcs. So in particular, I think we're looking at this one, arc sine of x over a. So this would be arc sine of x over 4 from 0 to 2. So this would be arc sine of 2 over 4. Take arc sine of 0 over 4. So this is just arc sine of 2, take arc sine of 0. So that should be a half, sorry. Half. And we can see what that is. So if we look at inverse sine of a half, we can see that's pi over 6. And I reckon the other one will just be 0. So let's go inverse sine of 0 at 0. So this is just pi over 6. All right, this one, 6 over 9 plus x squared. So in general, we're after one that looks like this, a over a squared plus x squared. So the way we can write this is, well, the integral of 6 over 9 plus x squared dx is, well, it's 2 times 3, 6, and this is 3 squared plus x squared there. Now, the reason I write it like that is I can pull the 2 out the front of the integral, and now this looks like what the arctan one was supposed to look like. 3 on the top, 3 squared on the bottom. That's a and a squared. So this is 2 arctan x over 3 plus c, and c is a real number. Wonderful stuff. Okay. All right. Now, this is where it gets very spicy. You'll notice that in all these formulas, you don't have any that have like an a in front of the x squared. It's always just normal x squared, so we have to adjust here. So the integral of minus 3 over root 9 take 4x squared, this would equal. Now, there's a couple ways you can do this, but what I want to do is deal with the x. So I'm going to pull out 4 as a common factor in the square root. What I'm left with in that last bit is x squared. And what I'm left with for the first term is actually 9 over 4. And I'm still going to have 3 on the top, and we're still going to have dx on the end. Yeah, how does this work out? Well, so that is root 4, and it's root of 9 over 4 is actually just 3 halves squared, just like that, dx. And then this is 3 over 2 that we can pull out, because root 4 is 2. Okay, so we get that, and then we can line it up with our formula. So I think if we had this formula, it sort of looks like that, the arc-cos formula. So this is just going to be 3 over 2 here. And this will be arc-cos of the flipped version. So arc-cos of 2/3 of x plus c. C is in R, just like that. Okay, so that's how that one works. Just making sure, yeah, it's x over a. A was 3 halves, so we get 2/3 times x. Another alternate correct answer would be minus 3 over 2, arc sine of 2/3 x plus c. C is in R. Both of these are absolutely correct. You'll notice that if you graph both those, the functions aren't the same function, but they're sort of overlap, like they're different heights of the same function. And just in case you don't believe me, there they are. And because you got a plus c value, depending what that c value is, you can actually get them to line up. So yes, they are both correct. All right, moving on. Integration by substitution. So we need a good u substitution for this. I'm going to pick u is 1 plus x squared. And then du dx would be 2x. So this integral is du dx root u dx. So this is root u du, which is u to the half du, which is u to the power of 3 halves. You want to divide by 3 halves, but that's the same as timesing by 2/3. Plus c. C is in R. And then that is 2/3, and then u was 1 plus x squared to the power of 3 halves. Beautiful. Okay, sine of root x over root x. This is a really tricky u substitution. Remember, u is the thing that's trapped. I'm actually going to set u equal to root x. So that would be x to the half. And so du dx is half x to the minus a half, which is 1 over 2 root x. So that's du dx. We don't have 1 over 2 root x, but we do have 1 over root x. Sometimes I like to rearrange this so that 2 times du dx is 1 over root x. And so here, this integral will become sine of u. I have like 1 over root x there. You can imagine like a 1 being on the top. So I'm going to replace that with 2 for u dx. dx. The dx's cancel, so you get, well, they don't technically cancel, but they sort of do. It's 2 sine of u du anyway. So this is 2 cos of u, and it's got a minus sign in front of it because sine goes up to minus cos. These in R. So that's minus 2 cos of root x plus c. Now, I'm not going to do this for every question, but I do encourage you to actually check this. So if f of x was minus 2 cos of root x, you would get f dash of x being 2 sine of root x. Sine's the baby. So that would be half x to the minus half, which is the 2.5 will cancel, so you get sine of root x over root x. Important to double check that. Okay, integration by parts. So integration by parts formula looks like uv dash is uv, take the integral of u dash v. So we got to figure out what our u and our v dash will be for this one. Now, I don't know how to integrate log of 5x, so I'm guessing that that's not going to be my v dash because you have to integrate v dash. So maybe let's try x cubed for the u. No, sorry, my bad. Let's try log of 5x for the u. And then u dash can be, well, it's 5 over 5x. So it's the derivative there on the... Yeah, so 5 on the top is the derivative, and then 5x on the bottom. The 5s will essentially cancel, so you get 1 over x for u dash. V dash is going to be x cubed. So v would be the integral of that, which is x to the 4 over 4. So let's see if we can get this. The integral of x cubed, well, I might actually start with the integral by parts formula. So uv dash is uv, take the integral of u dash v. So that is x cubed log of 5x is log of 5x times x to the 4 over 4. So that's the uv bit. And then u dash v. So that's 1 over x times x to the 4 over 4 dx. Okay, that's a lot to deal with, but it's not too bad. X to the 4 over 4 log of 5x. I just like it around that order a bit better. And then this is take the integral of, the x on the bottom will cancel with one of them on the top. So it's the integral of x cubed over 4. And then that's x to the 4 over 4 log of 5x. Take, now x cubed goes up to x to the 4, and you're dividing by 4 again. So that's over 16 all up. Plus c. C is in R. Cool, all right. Next one, e to the x cos x. Now this is a very pesky integration by parts. I'll start out with the formula. So u dash, I always get it the wrong way around. uv dash is the integral, is uv, take the integral of u dash v. We need to figure out what u and v dash are. In this case, it actually doesn't really matter. So I'm going to set v dash as cos x, and that would tell us that v is sine x. U is e to the x, and so u dash is e to the x. So you're going to get uv. So integral of e to the x cos x is uv, so that's e to the x sine of x. Take the integral of u dash v, so that's e to the x sine of x. And we actually don't know how to integrate e to the x sine of x. So what we need to do is actually integration by parts again. So we're going to get e to the x sine of x here. Take the integral of, well, sorry, not the integral, take. Now I'm just going to write this as uv, take the integral of u dash v. And for this one here, we've got to pick what our u and v dash are. So here u was, make sure I get this right around. It doesn't really matter too much, but let's pick u as sine of x, just so I'm dealing with less negative signs. So we're going to get cos of x there. And then, let's see, v dash would be e to the x. So v is e to the x. Good. All right, so this will become e to the x sine of x take. Now, uv is... Actually, I lied. I think I do have to pick it the other way around. That's my bad. So e to the x sine of x here. We'll pick e to the x and e to the x, and we're going to go sine of x for v dash, and we're going to get cos of x with a negative sign for v. So that's e to the x with minus cos of x, so minus e to the x cos of x there. And then u dash v, so that's going to be e to the x with minus cos of x again, dx. Now, this is just e to the x sine of x plus e to the x cos of x. Two negatives make a plus, sorry, three negatives, one from the brackets, one from before the integral, and one from in the integral, e to the x cos of x. And on the left-hand side, we actually had e to the x cos of x dx. I should have had a dx up there as well. And I might just fill that in on each line, just for completeness. Okay. Now, what's going on here is we still don't know how to do that integral in the end, but you might notice that this integral and that integral are the same. So what I'm going to do is I'm actually going to be adding on e to the x cos of x to both sides. Okay. So we'll see that. And that's going to give us 2 times the integral of e to the x cos of x equals e to the x sine of x plus e to the x cos of x. We really should have a plus c. I'll add all that in later. And then that would give us e to the x cos of x is half of all that. So e to the x sine of x plus e to the x cos of x all over 2. I'll put a plus c at the end. This would be a different c, so I'm just going to call it c1. And then we can have plus c1 all the way up through here. So plus c1, plus c1, plus c1, plus c1. And the reason the c is different here is because I've halved it. So c is c1 over 2. Okay, so that's how we deal with that. Pretty awful process, but we did it. Okay, speaking of awful questions, consider this one here. We need to show that the intersection of those 3 points. Okay, so we're going to set f of x equal to g of x. So that tells us that 3 over 1 plus x squared should equal 3 take x squared. And we can sort of deal with that. So we can cross multiply, sort of. So I'm just going to go 3 take x squared times 1 plus x squared. And then that's going to give us, we can FOIL this. So I'm going to get 3 plus 3x squared when I FOIL it out, minus x squared. And let's see, take x to the 4, just like that. And conveniently, the 3's actually cancel off. So I'm left with 0 equals 3x squared, take x to the 4. So 0 is, that's just 2x squared, take x to the 4. And let's see, I might factor it out. So 0 is x squared, and we get 2 take x squared there. Now, using the null factor law, x is 0, or 2 take x squared is 0. So this is the null factor law. Basically, what that tells you is if you got 2 things times together to give 0, then one of those 2 things is 0. Now, I might actually just, so x is 0, or 2 take x squared is 0. Therefore, x squared is 2. Therefore, x is plus or minus root 2. So those are the 3 intersection points as required. And you can sort of see on there. So this is about 1.41, which is root 2. This is minus 1.41, which is root 2. And then this one is just 0. So that's the 3 spots that the functions are intersecting. use technology to calculate, oh, we haven't actually shaded the area, shade the area between the functions. So if I want to do that, just pick like a nice color. I might just go green. So that's the total area from B. And we want to calculate the area that we shaded in B. So what I'm going to do is graph these two functions. So I might just delete that one out. And we're going to go 3 over 1 plus x squared. And 3 take x squared. And we'll draw those, and it should hopefully look like what we got. So let's go into our window. We'll match the window the question gave us, so -3 to 3. And y can go, let's go -1 up to 4. And that should give us a pretty close match to what the graph actually looks like. Yes. And then if we go gsolve integral mixed, and I click the first entry, and I scroll across to the very last one, then I'm hoping I get 0.867 or 0.868. Just for something later, I'm going to point out that if you integrate just half of it, so if you go 0 up to √2, that is just half the total area, so 0.433. That's something worth just keeping in mind for later. Okay, so we've got a few different pairs of functions. This one I had was p equals 3, and that number is the p. So we're basically just going to look at this pattern, p equals 4, 5, or 6, etc. And we might get some intersection points. So f of x, might just say this in full. So let f of x equal p over 1 plus x squared, and g of x equal p take x squared. So for p in R plus, f of x and g of x intersect at, so it's going to be x equals 0, √p, and minus √p. So those 3 points. You can see when it's 6, we get √5. When it's 5, we get √4, which is 2. When it's 4, we get √3. And we can prove that conjecture. So to prove our conjecture, so we want to set to find the intersection points. F of x equaling g of x. So that would tell us that p over 1 plus x squared equals p take x squared. So that would tell us p equals p take x squared and 1 plus x squared. And so p is p plus px squared take x to the 4. And we can cancel off the p on both sides. So that's 0 is px squared take x squared. Oh, that is my bad. The conjecture should be root of p take 1. I just remembered that. It's always 1 less. So 5 is 4, 6 is 5, 4 is 3. My apologies. Anyway, take x to the 4. And 0 would be, so this is p take 1 with the x squared. Take x to the 4. And what I can do is pull out a common factor. So 0 is x squared with p take 1 take x squared. And so either x is 0 or p take 1 take x squared is 0. So x squared is p take 1. So x is plus or minus √p take 1. Cool. So we proved that conjecture, and now we need to prove the area formula. That's horrible. So as I said before, you can get this area by just taking the right half and doubling it, because this thing is symmetric. And I actually make a note in the question that you can do that. And if you ever want to prove that, the way that you'd formally prove that is these original functions only have x squared in it. So you would want to prove that f of minus x just equals f of x for any x value you can put in. And that's just true because minus x squared is the same thing as x squared. So any negative x values are going to be the same as the positive ones. This is something called an even function when this relationship is true. We just don't do even functions in the course anymore. But you can still use this cheeky trick, just half the area and double it. So that would tell you that area is the integral from 0 to the intersection point, root of p take 1, of, I think g of x is actually on the top here. Yes, it is. The red one's on the top. So this will be g of x minus f of x. Okay, now we can put in all the things we have. So this is 0 to root of p take 1. G of x was the red function, 3p take x squared. And I'm going to be taking away p over 1 plus x squared. Okay, when I do that, we can actually integrate each piece pretty easily. So the first one is px. The second one is x cubed over 3. The third bit, we don't have a nice formula, but it's actually the arctan one. 1 over 1 plus x squared gives you arctan. It's just we've got a p out the front. So p arctan of x. And you might be clued into the fact there's an arctan in the formula here. So we're going to close that bracket and integrate from 0 up to root of p take 1. And my apologies, I should have times that by 2 because you have to double it to get the whole area. So we're just going to leave a 2 out the front with all of our working. Okay, so this would be 2 times p root p take 1 take p take 1, well, the square root of p take 1 cubed over 3 take p arc tan of root p take 1. Now we're going to put in the 0. Take, I might actually do this down here. Take p with 0, 0 cubed over 3, and p arc tan of 0. Now, everything in the last bit with the 0 is just going to be 0, but I don't want you to always assume that. Sometimes it's not the case. So this is 2p root p take 1. Root of p take 1 cubed is, so you sort of get root of p take 1 squared times root of p take 1. But root of p take 1 squared is just p take 1. So you get that. And you get p arc n of root p take 1. Okay. We're almost there. Okay, so let's see. This is, I might just write out the same thing again. So 2p root p take 1. Take p take 1 root p take 1 all over 3. Take p arc n of root p take 1. And that should have a bracket around the whole thing. There we go. Okay. Now, the trick for the first two terms is to pull out a common factor of root p take 1. So what we're going to be left with, we'll put root p take 1 on the very end. But it is p take 1 over 3. Okay. Now, that would be 2 p take p over 3 plus 1 over 3. Root p take 1. Okay. This becomes 2. Now, p take p over 3, that's like 1 take a third. So it's 2/3. So 2p over 3 plus 1 over 3. Root p take 1. Take p arc tan of root p take 1. And then this, we can just combine the fraction together and we can sort of bring the 2 in at this point as well. So this would be 2 lots of 2p, so that's 4p, plus, and then 2 lots of 1, so that's 2, all over 3. Still times it by root of p take 1. Take, and then 2p, so 2p arc tan of root p take 1. Hey, we did it. Excellent. So my final answer should have that sort of under a big fraction, but as required. I guess it was a proof question, so we can do that. Yeah, awful stuff. I'm not going to lie, that question is quite difficult, but that's how you do it. Find the volume of the solid created by that shape when you go around the y-axis. So conveniently, I've got a graph there. So if we go from 0 to 2, I'm actually just going to fill in this question first. But you go from 0 to 2, and we're going to sort of sweep around that shape there. So that would be a mark for that bit. It's like a bowl shape. Find the volume of the solid related. So volume is pi integral from c to d x squared to y when you're going around the y-axis, which we are in this question. So if y is x to the 4, that tells us that x is the 4th root of y. So if you want, that tells us, well, that tells us what we need for this. Also, C and D are y values. So if x is 0, y is 0 to the 4, which is 0. And if x is 2, y is 2 to the 4, which is 16. So you can see that we're going to go from y is 16, and we're going to start y is 0. So that's going to be the bounds on our integral, 0 to 16. We got the 4th root of y, and we got to square it to y. And we're going to put a pi out the front. Okay, the 4th root of y squared, so it's square root of y, that's what it is. You can think of this as y to the quarter squared, and you can times those two numbers, so you get a quarter times 2, so you get y to the half, which is root y. Okay, and that is 0 to 16. So really that's pi. Well, technically I don't even ask you for the exact value or working or anything, so you could chuck it into your calculator, but I'll do it this way for completeness. That's y to the half, so you get y to the power of 3 halves over 3 halves, or in other words, times 2/3. This is from 0 to 16. This is pi. You're going to get 2/3 of 16 to the power of 3 halves, and 2/3 of 0 to the power of 3 halves. Now, 16 to the power of 3 halves, what that means is you take the square root of 16 and then you cube it. Square root of 16 is 4, and then you cube it to get 64. Just in case you don't believe me, 16 to the power of 3 halves is 64. And if I times that by 2/3, I should get more than that number. As a fraction, that's 128 over 3. So 128 over 3 pi is the final answer, because that last bit's 0. Which roughly equals, so if we times that by pi, that's helpful Casio, 134 units cubed. Okay, dokie. Next one. We're going to prove the volume of a cone formula in this one. So we've got to explain why this line has that. So the equation of a line usually looks like y equals mx plus c. M is slope. C is the y-intercept. M is, let's go, y2 take y1 over x2 take x1. So you pick 2 points. Here, we can pick 0, 0, and I think our other point is RH. So this would be h take 0 over r take 0. So it's h over r. That's our m value. And c is 0, so the y-int is 0. Therefore, y is h over rx, as m is, well, h over rx plus 0. So, yeah, y is h over rx. It's a 1-mark question, so as long as you got something there, you're fine. Now we need to do volume around the y-axis again. So volume around the y-axis, again, it's the integral from c to d of x squared dy. And we need all our values. So y is h over rx. Therefore, x is r over hy. We just sort of times like that. So this would be the integral from 0 to h, because those are the y values. And we've got r over hy, and we're going to square that to y. And we're going to put a pi in front of it. So this is pi. So this is 0 to h, r squared over h squared times y squared dy, which would be, I'm just going to pull the pi r squared over h squared out the front, but you get y cubed over 3 from 0 to h. And so you get pi r squared over h squared, and you're going to get h cubed over 3, take 0 cubed over 3. So a lot of stuff is going to cancel out. So you're going to get pi r squared, well, that last bit 0. So h cubed over 3h squared when you times it all out. And then that is going to cancel out a little bit. So you're going to get pi r squared h over 3, which is the volume of a cone formula. Okay, last time we got a modeling question. So we've got to model the 4 line segments above. Now, the thickness of the thing is 0.1 millimeters. So at any point here, that thickness is 0.1. Looks like that top line there is just y is 0.2. And the line underneath it is y is 0.1, because that's sort of the scale on the axis here. So y is 0.2, y is 0.1. Now the bits out here, we can use the same sort of method from before. So this appears to be 2 and 0.2. And then this bit up here appears to be up to 1.2. So 4 and 1.2. So the top line, m is going to be the y values. So 1.2 take 0.2 all over 4 take 2. So that is a half. And c, well, we don't know what c is, but we know that y is half x plus c, and we can sub in a point. So we can sub in 2 and 0.2 into that equation. So you're going to get 0.2 is half x plus c. Yep, so we want to do that and sub in the x value. So the x value was 2. So 0.2 is 1 plus c. So c is 0.8. Minus 0.8. You can sort of imagine tracing this line back. You probably would hit about minus 0.8 if you do that with the same slope. So that's one of the lines. So y is half x take 0.8. And then the other line is just, because the thickness is 0.1, the other line is 0.1 lower. So the other line is y is half x take 0.9 if you do that one. Okay, so that is the 4 that we've got. So we've got that, and that. So we've got to use the 4 equations. So for the first bit, volume is pi times the integral from, now that first segment goes from 0 to 2. Our top equation there is 0.2, so 0.2 squared take, and our bottom equation is 0.1 squared dx. We can work that out in a second. And our second equation, the volume is, well, we're integrating from 2 to 4, and we're looking at the top equation is half x take 0.8 squared, and half x take 0.9 squared. So those are the 2 integrals we're supposed to do, and then we can just do those in integral mode on the calculator. So we'll chuck a pi out the front. 0.2 squared, 0.1 squared, and we're integrating from 0 to 2. So that volume is 3 out of 50 pi. And I might just call this volume 1 and volume 2. Volume 2 is similar integral. So I might go just 0.5x take 0.8, and we'll square that. Take, and 0.5x take 0.9, and we'll square that. Make sure if you're using an emulator like this, you press the X button and you don't type X, otherwise you get into trouble. We've got to integrate it from 2 to 4, and we're supposed to times it by pi as well. All right, 13 over 50 pi. So volume is volume 1 plus volume 2, which is 16 over 50 pi, which roughly equals, so 16 pi over 50 should be 1.01. And that's the test done.